Okay, continuing in the kinetics unit, we're going to talk about the rate expression. Things that we want to accomplish in this screencast are to distinguish between the terms rate constant, overall order of reaction, and order of reactant with respect to a particular reactant, be able to deduce the rate expression given experimental data, solve problems with the rate expression, and sketch, identify, and analyze graphical representations for zero, first, and second order reactions. Okay, so let's talk about concentration and rate. One can gain information about the rate of a reaction by seeing how the rate changes with changes in concentration. Okay, well, what does that mean? Well, if we have data, and let me fix this data, the concentration will be in moles, decimeters to the negative third, moles, decimeters, negative third, and the rate is going to be expressed as concentration, which is moles to the decimeter negative third to the inverse seconds. Right? Here is data. We have run 6 experiments changing concentrations. Okay, some of them you notice are the same, and then they differ, and we can see the impact on the rate. The equation that we're working with is ammonium ion reacting with the nitrite ion to form nitrogen gas and liquid water. If we look at experiments 1 and 2, we notice that the concentration of the nitrite remains the same. So the concentration of the nitrate is not going to have any effect on the change in the rate. But I did double my ammonium concentration. Looking at the rate, my rate also doubled. Okay. Now, when we look at experiments 5 and 6, we notice that this stays the same, so the concentration of ammonium is not going to have any effect on the rate. We notice that the concentration of my nitrite is multiplied by 2, and again we should see that the rate is multiplied by 2. Okay, what do we do with this information? Well, what it means is that the rate is proportional to the ammonium concentration. The rate is also directly proportional to the nitrite concentration. So we can state that the rate is proportional to the concentration of the ammonium times the concentration of the nitrite. We can write that proportionality as an equality by putting in what is known as the rate constant. This expression is known as the rate law. It's known as the rate expression, and K is the rate constant. This K remains constant for any given temperature. If I change the temperature, I'm going to change that K. All right, so for any given temperature, if I know the concentrations of the reactants and I know the K, I can calculate the initial rate. If I know the rate and I know the concentrations, I can calculate the K. There's a lot of things that we can do with this equation. All right. So the rate law, also known as the rate expression, shows the relationship between the reaction rate and the concentration of the reactants. The exponents on those concentrations give us the order of the reaction. So if we look at the rate law that was given before, the power on the ammonium is 1, the power on the nitrate is 1. So we say that this reaction is first order with respect to the ammonium ion. It is also first order with respect to the nitrite ion. The overall order can be found by adding those exponents on the reactants in the rate law. Okay, so by adding the powers, I can get the overall. So if it's first order in ammonium, first order nitrite, 1 plus 1 is 2. The reaction is second order overall. Looking for general terms, the general equation for the rate law or rate expression for the equation A plus B going to C is rate is equal to the rate constant, A to some power m, concentration of B to some power n. By the way, These orders need to be found experimentally. You cannot use a balanced equation to find them except in special circumstances. Cannot use a balanced equation. Have to do it by experiment, or if you're given some special information about the equation, which we'll talk about later. All right, so but anyway, getting back, K again is the rate constant, M is the order with respect to A, N is the order with respect to B, M plus N is the overall order. You can have orders of fractions, and you can have negative orders. So keep that in mind. You can have fractions. M and N could be a fraction. It could also be a negative. All right, so if we look at these equations, what we want to do is find the overall reaction orders for these equations and what are the units for the rate constant. Right? Well, the overall order for this equation here is 1. So this is first order overall. If I'm looking for the units for the rate constant, we know that rate has the units of mole, decimeter to the -3rd, and then time to the -1. Be aware that it's sometimes in seconds, sometimes in minutes. If I want to find the units for K, then K is going to be the rate divided by the concentration of N2O5 dinitrogen pentoxide. I know that the units for rate are moles, decimeters -3, seconds -1. Concentration for dinitrogen pentoxide will be moles, decimeters -3. Moles cancels, decimeters -3 cancel. Units for K for a first order system are inverse seconds. Looking at the second problem, okay, the overall order well, it's 1 plus a half, so it's 1½ That's weird. Okay, so looking again, K is equal to the rate over the concentration of CHCl3 and Cl2 to the 1/2. So, well, rate I know is moles, decimeters -3, seconds -1. Concentration for the first one is moles, decimeters -3. For Cl2 to the half, it will be mole to the 1/2, decimeters to the -3/2. So the units for K in this case, these moles cancel, this cancels. I get moles to the -1/2, decimeters to the 3/2, and seconds to the -1. Those will be my units for K. If you have any difficulties getting from here to here, you need to see me for a little refresher in powers. Okay, so looking at experimental data and changing our units to IB units, concentration of A in moles, decimeters -3, moles, decimeters -3, and then the initial rate will be moles, decimeters -3, and we'll do seconds -1. So using this data, determine the rate law for the reaction, the rate constant, and the rate of the reaction when the concentration of A is 0.05 molar, moles moles per decimeter negative 3 and 0.1 moles per decimeter negative 3. All right, so, well, do this problem, bring it into class, and we will review it. Same with this, we'll look at that in class. Let's look at graphical representation of reaction kinetics. If I have a zero order reaction, and they do exist, the rate of the reaction does not depend on the concentration of the reactants. So if we're looking at a graph of concentration versus time, we'll get a straight line down. And if we look at rate versus concentration, a straight line, because the rate does not change with the concentration, it remains steady. And again, concentration over time is just direct. Looking at first order, and you are expected to be able to identify the differences in here. Rate is directly proportional to the concentration of reactant A. Concentration versus time gives me this slope. Rate versus concentration gives me a straight line. Second order, again, rate is directly proportional. You get a little bit of a different kind of curve for concentration versus time, a little steeper. Rate versus concentration gives you an exponential curve like that. So again, you need to know these. You need to know when you're talking about concentration versus time, what the slopes look like and the differences between them, and then the rate versus concentration. We're going to stop the screencast here and we'll pick up with half-life.